So today we are going to look at an important idea called power and understand how it's different from energy and work. So, quick review, there are many ways to measure energy. The most common way is the joule, and that's what we've been using to measure energy. But there's also the calorie, and that's a common unit that's used in the USA at least for food and for heat, like so you might have encountered it in chemistry. The BTU is also used in the USA, mostly for heating and cooling and air conditioning applications, or maybe grills and stoves and ovens and things. A kilowatt hour we're actually going to touch on today, and it's used to measure electrical energy. And it's kind of a goofy looking unit, so we'll talk about what it means. And then the electron volt you've encountered in chemistry, so I'm adding it in here. There are lots of other ways to measure energy, but these are some of the common ones you might have encountered so far. The ones that I think you should know are joule, which is our standard, and the calorie is also a way to measure energy, and we have a conversion factor in our toolbox to convert back and forth. You also might have encountered in chemistry kilojoules per mole. That's another way to measure energy, which is common in chemistry. All right, so a quick word about potential energy. If you find out that somebody's net worth is negative, what does that mean? Well, if your net worth is negative $300,000, it means you are in debt. You're trapped. You need $300,000 to pay back just to get back to being broke. So you have negative self worth, it means you are trapped. We would say you are bound or you are trapped. So it turns out that potential energy can also be negative. Kinetic energy can never be negative because kinetic energy is energy of motion and you can't go slower than stopped. So kinetic energy cannot be negative, but gravitational energy can be. So imagine that you fall in a hole. So here is our zero reference for energy, and if you were in the hole, your gravitational potential energy is negative. Let's say Mr. Gecko here's gravitational potential energy is negative 10,000 joules. What that means is he's got to somehow pay back a debt of 10,000 joules just to get back to having no energy at all. So if he was up here, he would have no energy, no kinetic, no potential. So he actually has negative potential, and so we would say he's in a hole, or he is trapped, or he is in a bound state. We use bound state in chemistry a lot. It means you're stuck, you're trapped, you're stuck there. Okay, so gravitational potential energy means an object is stuck there and is not free, and you have to pay your energy debt. So in this case, 10,000 joules just to get free. So it turns out that we aren't free either. We are stuck on this earth, and we can't just hop off the earth and wander around the universe because we are stuck in a gravitational hole. And so we call these sometimes gravity wells. And so here's a cool little visualization. This is from the XKCD comic, which shows sort of the size of the gravity well. So we're over here on Earth, and we have a pretty small well, but it still seems like a lot to us. So the top of this line right here is the surface of the Earth, and we are in a hole. We would need to pay back our energy debt. We would need to gain lots of energy to escape from Earth and maybe go to the moon, which is right here. We would need to, however, that we're not completely free. We're still bound to the sun. We have potential energy because of the sun, and we need to add more energy to get to Mars, and even more energy to get to out past Mars' orbit. And then there's this huge gravity hole of Jupiter, and you can see how big it is. So the gravity hole of Jupiter is enormous compared to that of the Earth. So those are just fun ways to think about the fact that when you're on a planet like Jupiter, you have an enormous negative potential energy, and you've got to pay back a lot of energy to get off. So I don't think we'll ever be able to land a rocket on Jupiter and then escape and get back. Getting back from Mars isn't too much work, but getting back from Jupiter is enormous. So another place you might have seen potential energies is in the electron level diagrams in chemistry. So if you haven't seen this, don't worry about it. But if you have, you might remember that electrons are bound to the nucleus. They're attracted to the nucleus. And if you want to take this electron off and pull it away, you've got to pay back some energy. So we call these the electron levels. So maybe you remember the ground state level when n is 1. So that's this guy right here. Its energy was negative 13.6 electron volts. So there's electron volts, a way to measure energy, and it's negative. That means it's bound. You have got to add 13.6 electron volts of energy just to get this guy free from that positive charge. And then electrons in other energy levels take less and less energy to get free. So that's maybe how you would have encountered some negative energies in chemistry. Again, you don't need to know this for physics. I'm just connecting to what maybe you've already seen. So the ionization energy is a measure of how much energy it takes to remove the outer electron of an atom. And the ionization energies for helium, neon, argon, krypton, for example, are huge. It takes a lot of energy to get that last electron off. And so basically, it doesn't really happen very often, and we say these are the noble gases. Things like lithium, sodium, and barium, it is very easy to get that last electron off. They don't have much energy debt that they have to pay. It only takes 5 electron volts of energy to rip off that electron from lithium. And so lithium very often loses its outer electron, and that's why it has a positive charge. So whether things have a negative charge or a positive charge depends on how much energy it takes to rip off that last electron. So that's, again, measured in electron volts. Okay, so now we get to the topic for today, which is work, energy, and power. So a reminder, work is the energy you have to transfer from one form to another. So if I'm going to take a bunch of water in a lake and pump it up to a water tower, I've got to add gravitational potential energy to that water. Okay, so work is the transfer of energy from some form, maybe electricity, to gravitational potential. I'm going to run a pump. I'm going to pump the water from my reservoir here up into the tower. So now the water has gravitational potential energy, and it got the energy from the electricity. So the work was the transfer of that energy. Now, power is a little bit different. It's not the energy, it's the rate that the energy was transferred. So power is a rate. It's how much energy is transferred per unit of time from one form to another. And so this is the equation we're going to use, and this should be in your toolbox. It's the last equation for the unit. It says that the power, the rate that we transfer energy, is equal to work divided by time. So remember, work is the energy we transfer, divided by the time it takes to transfer it in seconds. That's the power. So power is measured in watts, which is just how many joules of energy are transferred every second. So that's what we're going to use. The watt is joules per second. And it helps when you see the word watt to think joules per second. It'll remind you it's not the same as joules. So watt is a unit of power. It is not a unit of energy. So the standard unit is a joule per second. There's some other units of power that you might run into. A common one is the horsepower. So back in the days when people were introducing the steam engine, it was helpful to compare your new steam engine with farm animals because farm animals were doing all of the work of lifting ore out of the mine, and a mule could do a certain amount of work in a given amount of time. And so we called it a horsepower, and so that's kind of generous. It's really a mining mule. But it turns out that 1 horsepower is the same as transferring 745 joules of energy every second. Okay. Another common one is calories per minute. If you're on the workout machine at the fitness center, you might see that your power output is measured in calories per minute. So remember, calories is that unit of energy divided by a unit of time is the unit of power. If you're looking on your water heater, it might say how many BTUs of energy are transferred every hour. And in general, any unit of energy divided by a unit of time is a valid unit of power. But please remember, energy is not power. So this conversion should be in your toolbox. I think we've already used it once, but it should be there. All right, so let's think about some examples of how we transfer energy. We have electrical energy. We need to store it in our phone, so we have a power supply. This isn't really a power supply. It just transfers power from electrical energy at 1 voltage to electrical energy at a different voltage. But this little power supply, which you might charge your phone with, is somewhere between 5 and 10 watts. The original ones were 5 watts. The newer ones are about 10 watts. And if you get a really brand new phone, you don't even get a charger with it anymore. But it's telling you how many joules of energy can be transferred to your phone every second. So 10 watts means 10 joules every second. My iPad has a slightly bigger charger, and it's rated at 20 watts. So in this case, it can transfer 20 joules of energy every second. And if you've got a MacBook charger, it's even bigger. It's somewhere between 45 and 100 watts, depending on how new it is. You can look up on Amazon replacement chargers for your MacBook, and you can pick what power you'd want. The higher the power, the more energy it transfers every second. Okay? So that's just telling you the energy transfer rate, the power. So here's some examples of light bulbs that you maybe have heard of before. An old-fashioned light bulb is called an incandescent bulb. So current runs through this little tiny wire and it gets really hot and it glows. The problem with incandescent light bulbs is they produce a lot of light, but they also produce a lot of heat. So for example, a 60-watt light bulb transfers 60 joules of energy every second from electrical energy to light and heat. The problem is, out of your 60 joules every second, you're only getting about 8 joules every second of light. The rest of it is heat. The majority of it is heat. So these things are really just heaters that happen to give off a little bit of light. And they're not very efficient because it takes 60 joules every second to produce 8 joules every second of light. A more efficient version is the compact fluorescent light bulb. So CFL stands for compact fluorescent. These don't use nearly as much energy. They're about 20 watts. They still give you the same amount of light, about 8 joules every second of light, and they give you about 12 joules every second of heat. So they're about 20 watts total, 20 joules every second, and they produce the same amount of light as an incandescent bulb, but with about 1/3 of the energy every second being used. The newest kind of lights are LEDs, or light emitting diodes, and these generate very little heat. So they use, for example, 10 watts or 10 joules every second of energy. 8 of that gets converted to light, and only 2 get converted to heat. So we say these are very cool. They don't produce much heat. Almost all the energy that goes into them gets converted to light. So these are much more efficient. The problem with these, of course, is they cost a little more. So these are like $12. These cost like $5, and these are 25 cents. These guys are really cheap, but they also don't last very long. You can see they only last about 1,200 hours, whereas the LEDs last a long, long, long time. So there's a trade-off there, but obviously these are more efficient, and most of the lights nowadays that are installed are LEDs just because they're so much more efficient and they don't produce a whole bunch of heat. It's not bad to have heat producing by a light bulb if it's the winter time, but in the summertime, if you produce extra heat from your light bulbs, you also have to run the air conditioner more. Okay, the other thing that's bad is these compact fluorescent lights, they contain mercury vapor, so you have to dispose of them carefully and you have to recycle them. You don't just throw them in the trash. And so they're somewhat harmful to the environment because of the mercury vapor that's used. All right, so a quick review of vocabulary. Energy is the ability of a system to do something for us. We measure energy in joules. It's the accounting system of the universe. Work is the transfer of energy from one form to another. And since energy is measured in joules, work, the transfer of energy, is also measured in joules. Power is the rate that energy is transferred. It's how many joules every second are transferred, and it's measured in joules per second or watts. So we just got to keep those 3 things straight. You might want to jot those down in your toolbox just to keep them straight so you remember which one's which. Now, it's really easy to get confused, so let me just make sure I can point this out. When we are writing equations, as a variable, W means work. So in this equation you just got today, the power is the work divided by the time. W stands for work in equations, and that work is measured in joules. But when we are talking about a unit of measurement, W stands for watts, and watts is the unit of power. So a watt is a joule second. So if I say the power of a light bulb is 100 watts, this W is the unit watt. In an equation, W is the variable for work or energy transferred. So you just got to make sure you keep those straight. That's easy to get confused. You see a W and you think it's watts. It's not true. Here, this W means work or energy transferred. All right, 3 examples. I've got a lawnmower. It can do 14 million joules of work during the 60 minutes it takes me to mow my yard. Of course, a million means 10 to the 6th. So let's figure out what the power of my lawnmower is. So I've got a variable list. The power is what I'm looking for. The work is 14 million, or 14 times 10 to the 6 joules. And the time is 60 minutes, which is 3,600 seconds. So I'm assuming you can figure that out. We're simply going to evaluate our little equation, P equals W over T. Plug in our numbers, calculate it, and my mower is about 3.9 watts or 3,900 watts. So it transfers 3,900 joules of energy every second from chemical energy, gasoline, to kinetic energy, the spinning blade. All right, if I wanted to convert that to horsepower, this is how I would do it. I just want to show you, take your answer in watts, and you know that 1 horsepower is 745 watts. We put that in our toolbox. And so the watts cancel. We got numerator and denominator, and that's about a 5.2 horsepower mower. Okay, so a typical push lawn mower is about 5 horsepower or so. All right, now, before we do the next example, let's quickly look at power and energy. Power is the work divided by time. If I multiply both sides by T, I can say that the work, the energy transferred, is the power times the time. So, energy transferred, the work, is the power times the time. So if we transfer 1,000 joules of energy every second, so that's 1,000 joules per second, which is 1,000 watts, and we do that for an entire hour, that's 3,600 seconds, we can figure out how much energy that would be. We take 1,000 joules every second, or 1,000 watts, times 3,600 seconds, and that gives us 3.6 times 10 to the 6th joules. So joules per second times second just gives you joules. So 3.6 million joules is what we get, and we call this 1,000 watts is a kilowatt, and 3,600 seconds is an hour. So we call this a kilowatt hour. So 1 kilowatt hour is a unit of measuring energy. It's kind of weird because it's got watts in there, but it's a kilowatt hour. So 1 kilowatt hour is 3.6 million joules. And that's important because when we buy energy from the electrical company, they sell it to us in kilowatt hours. So anytime you see kilowatt hours, just remember that's 3.6 million joules. So I think that's in your handy conversions page, and if not, go ahead and put it in there. We're going to use it. So if you look at your electricity bill, or you can take a peek at the electricity bill that comes to your house, you might see something like this. The meter was read on October 15th. This was the number of kilowatt hours. It was read again a month later, and the difference is 924 kilowatt hours. So that's how much energy we used. And remember, each kilowatt hour is 3.6 million joules. So in Indiana, we pay about 10 cents for each of these kilowatt hours. So at 10 cents each, that's about $92 of electricity. There's a little extra here because there's some taxes and there's a connect fee. They charge you $10 a month just for connecting to the grid. But right now it's about 10 cents a kilowatt hour in Indiana. So let's calculate how much it takes to hair dry your hair, to blow dry your hair. I've got a hair dryer. It transfers energy at 1,800 watts, so 1,800 joules every second. We're going to run that for 8 minutes. And we want to know how much energy that takes. So you can draw your diagrams any way you want if they don't involve kinetic and potential energy. So maybe you want to make a little diagram showing the form of the energy. We're going from electrical energy to heat. That's what a hairdryer does, right? Here's our variable list. We know the power of the hairdryer is 1,800 watts, or 1,800 joules every second. And we know the time is 8 minutes. Oops, that should be down there under time. I'm sorry. That's 8 minutes, which is 480 seconds, excuse me. So this is the time, not the work. We're trying to find the work. So our plan is to solve P equals W over T for the work. We're trying to get W by itself. So we multiply both sides by T. So the work is the power times the time. We take 1,800 joules times 480 seconds, and we get a work of 864,000 joules. So it takes 864,000 joules of energy to run this hairdryer for 8 minutes. Okay? Now in NewPal, these kilowatt hours, these 3.6 million joules, they cost us 10 cents each. So we're going to use that as a conversion factor. If I take my 864,000 joules and I multiply by the conversion conversion factor, which is 10 cents for each kilowatt hour, or 3.6 million joules. I take this number divided by 3.6 e to the 6th, and I get 0.024. So it turns out it costs about 2.5 cents to blow dry your hair for 8 minutes using an 1,800 watt hair dryer. Okay, so that's just showing you how to do a conversion from energy to dollars, to cost, okay? And I don't think any of those are in the homework. I was just showing you that. All right, now let's put it all together with what we know from before. So if you want to stop right here and go solve the first 6 problems of the homework, you can. Problems 7, 8, 9, and 10 are a little harder. They involve conservation of energy and this idea of power. And so this example shows you how to put those two ideas together. So if you want to defer it and come watch it later, you're welcome to, or you can watch it now and then try to solve all the problems. Here's what we got. We got a truck. It's initially at rest. We got to get it moving at 25 meters per second, so about 60 miles an hour, and we got to do that in 8 seconds. We want to know how much power do we need? How fast do we have to transfer energy? So here's our variable list. I'm just going to plop it down there. H initial and H final are 0 because it's a level road. It says it starts at rest, so the initial velocity is 0. And we are told the time is 8 seconds and the mass is 2,500 kilograms. So our plan is going to be to do a couple things. First of all, we have to apply the energy theorem to build ourselves an equation, which looks like that. And that equation we want to use to find the work. We got to first of all figure out how much work do we have to do to get this truck moving. So we're going to solve for W. Now, a whole bunch of things are 0, so our life's going to be a little easier. H final, H initial, and V initial are all 0, so we can clobber those. That tells us the work is 1/2 mv final squared. Plug in our numbers, and it turns out the work we have to do is 781,000 joules. That's how much work we have to do. Now, the second step is we got to figure out how long it's going to, we know how long it takes, 8 seconds. We got to figure out what is the power. How fast do we have to transfer this energy? So we're just going to evaluate P equals the work divided by time. The work is 781,000. We got that from up here. The time is 8 seconds. We plug that in, and it turns out we need 97,000 watts, or 97,000 joules of energy transferred every second in order to get this truck moving at the speed it needs to be going. We don't really speak watts, so it's handy to convert this to horsepower. So the last part of the question says express your answer in horsepower. So if I want to convert watts to horsepower, I start with my energy transfer rate, the power in watts, and I use the conversion factor that 745 watts is the same as 1 horsepower. I've got to make sure that here the watts is in the denominator because it's in the numerator there. And when I do that, I get 130 or so horsepower to 2 significant figures. So we need a 130 horsepower engine to get this truck going 25 meters per second in 8 seconds. Okay, so that's using the energy theorem right here, as well as our new equation, power is the work divided by the time, in order to arrive at this solution. And the last 3 or 4 problems on the homework involve that idea. Okay, so you've got some problems to solve. This is the last thing in the unit. We'll review and then we'll have a test before we get to break. Okay, good luck.